Right, my name is Ahmed Tiamiyu. We wanted to, try to decipher what happens if we try to launch single particle at a time, which is very unique in itself. That was what we engaged on that project, and we started with a simple metal, which is copper, and then we decided to look at, hey, what goes in there, especially at this interface of this tiny particle and the substrate that it's hit. And in the process, we observed something very much interesting that what we thought we would see. That's where the laser comes into play. It's a very interesting all optics bed setup where the laser is very significant to help us achieve that. So apparently it just helps us to select single particle and then launch it just singly. It's a very difficult task. And that's not all actually. It's a different thing to launch the particle at that tiny speed, and it's a different thing to find it and then site specifically analyze it. That's where the real crucial work was. And this is what brought about the uniqueness of the research in itself. So the fact that we can go site specifically to lift out a tiny lamella from the impact site and then you characterize it is a big deal. So that way it helps us to really, by increasing the speed of the particle, we increase the strain at the interface of the particle and the substrate itself. So it helps us to get to those extreme processes, and then we can characterize with a lot of sophisticated equipment and get the information on how the grains actually evolve. Metallurgists can now intentionally target this condition to reduce the amount of materials required to develop the structure, for instance. And that can reduce significantly the energy consumptions and even the emissions of poisonous gas that I've mentioned earlier. So that's the benefit, I think, that it's bringing to the field.